in the room mic? Karen, can you hear me okay? Okay. So just a quick public service announcement for the people that are in 805 or in projects for 805. The semester is slipping away frighteningly quickly. So we're actually more than halfway to your midterm report, which is November 15th. A couple of Sundays off. So yesterday was Halloween. This is the best costume I saw. This was on Twitter, right? I didn't actually see this person. They didn't come around trick-or-treating. Do people know what this is? Vogue, scatterplot, articles on linear regression, slice up your null model. She's a statistical model. So, of course, when I saw this, what I did is I went to Google and I said, well, if people are doing a statistical model, right, there must obviously be, as a costume somewhere, the sexy statistical model. So I looked for that, and all I came up with was deep learning. So that's what we're talking about today, deep learning, continuing our lecture on that. So last week, if you recall, I gave a little bit of an artificial neural network overview. So I talked a little bit about scalability issues and how you train, okay? So that's kind of our nod to sort of the big data world. I talked about how they can be relatively expressive. And I talked about some of the tricks that we use in modern neural networks. And we spent a bit of time kind of walking through sort of a matrix vector implementation of a simple feed-forward, multi-layer neural network. So basically, this is the summary of the algorithm, right? So basically what you're doing here is you're basically sort of starting with some inputs, and you basically, at each point, you have a bias and a weight vector, and you pass the result of that through a sigmoid. And the way you do learning is you basically do gradient search. And the way you compute the gradients is with BackProp. So this is essentially the algorithm. We're computing this thing delta, which is basically an error signal. So first you compute the activation of the network. So you compute going forward what the network will compute. And here you're basically taking the activation at the previous layer. So in the 0th case, that's just the inputs. You're multiplying it by a weight matrix. Okay, so this can be a matrix of a mini batch of values. You multiply that by a weight matrix, you add a bias term, and you apply a sigma, and then you do it again. To train it, you go backwards. You start with the output layer, and you gradually compute the error, send the error signals back. Okay, the formulas for this are relatively simple. Again, we're taking the error signal at the next layer. We're basically multiplying it by the transpose of the weight matrix, and then we're doing an operation which involves the gradient of the sigmoid function. And at the end of the day, we have a gradient at every point in this network, and the ones that correspond to our bias nodes, we basically take the error signal for that, and so on. Okay, so it's a relatively simple implementation. So one thing I kind of mentioned briefly, the end of the lecture, or maybe at the beginning of the lecture in the outline, is that one of the reasons there's so much work in deep learning right now is because people have come up with tools that make it very easy to explore neural networks with different architectures. So rather than just using, a feed-forward network with multiple steps, people have explored many, many different relatively complex algorithms that you can implement by combining these differentiable units. So how do you do that? The way we do that is we use toolkits, right? So there's a bunch of toolkits that are out there. Just the ones that are most commonly known are Torch and Theano and TensorFlow. And what they do is under the hood, they all use a generalization of BackProp. So let's talk a little bit about what that is. So the big question is here, how do we generalize BackProp to arbitrary artificial neural networks? Okay, so listen up, because this is basically the next assignment. We'll be kind of getting down and dirty with this sort of techniques. So I'm going to start out by just giving you an example, all right? Here's an example of a function that we might want to differentiate, okay? So this is the function the way I would kind of like write it down in LaTeX, 2x1 plus x2 squared, okay? And I've also written in a particular representation we'll talk about in a little bit, where basically we have a bunch of intermediate variables, and each one is just a simple function of previously defined variables. So we start out x1 and x2 are the inputs. I'm sorry, x1 and x2 are the inputs. We start by adding x1 to itself, so I get 2x1, right? Then I add that to x2, and then I square the result. So at each step, I'm just applying a function of some inputs. So if I wanted to differentiate this, I mean, we could just do it. You know, it's like we sort of known how to do this for a long time. It's not complicated. If I did it right, this is 4x1 plus 2x2. You know, you use the chain rule a couple of times. So this is the different derivative with respect to x2. This is the derivative with respect to x1. So we know how to do this, okay? But what we want to do is we want to get computers to do this, which means we need to break this down into some very systematic kind of step-by-step algorithm. And that's where this representation here comes in handy, all right? So I'm going to basically sort of show by example first how we would use this representation of the function and differentiate this whole thing algorithmically, okay? So here are the first few steps. So let's say I want to find the derivative of this function f with respect to x1, the first input, okay? So what I'm going to do is I'm going to start off by using the chain rule. So this is the derivative of f with respect to x1 is the same as the derivative of z2 squared with respect to z2 times the derivative of z2 with respect to x1. That's the chain rule, okay? And I've also plugged in this definition here. So f is z2 squared, okay? So I plugged in f and I use the chain rule once, okay? So this is just a function of z2, all right? So I know there's this function I'm using in my list, in my representation. So let's assume I also know how to differentiate each of these functions. So I know the derivative of x squared. This is what it is, 2a, right? So I can just plug that in. So that's the next step, all right? Now I want to go a little bit further. I have another derivative to compute. This is a little bit simpler, right? So before I had f is determined in z2. Now I'm looking at the derivative of z2 with respect to x1, okay? So again, I'm going to basically plug in the definition, all right? So z2 is z1 plus x2, all right? Then what I want to do is plug in the derivative here. So this is the sum of two numbers. I know what the derivative of sum is, okay? So basically, I can plug that in and I'll get this, all right? We're left with two simpler things, the derivative of z1 with respect to x1 and the derivative of x2 with respect to x1, and so on, okay? So that's kind of as far as we got here, all right? But we can sort of take the next steps. So what I can basically do is plug in the definition of z1 here, okay? Right here, so z1 is x1 plus x1, and then I can plug in again the derivative of plus. So here it's getting a little bit messy because we got these big sums. So we're copying over this part here, that's the green part. All right, I'm going to copy over this part here and expand it out. That's the red part. All right, and now it's down to stuff that we basically kind of know, right? So we've got the derivative of a variable with respect to itself, that's 1. And the derivative of one input with respect to another, let's just assume that's 0, that the inputs aren't correlated. So then we can simplify, all right? And at the end of the day, what I get is 2 times z2 times 2, which is in fact the right derivative for the derivative of f with respect to x1, okay? So there's some notes I've written up for this section of the class. In the notes, I also go through f with respect to x2. And you can sort of see that most of the work is going to be the same, right? At some point, it's going to start breaking off. But most of the work is going to be the same. So when we're differentiating with respect to these several inputs, one nice thing about this particular algorithm is that there's a lot of shared work. All right. So this is my example. Now let's give you the actual algorithm here. So here's the algorithm in its generality, full generality. So we're going to start off, we've got a function of n variables, and we're going to write this down as a series of these assignment statements, okay? So this has a name. Sometimes it's called a tape, but that's a pretty vague name. Another name that people use for it is a Wengert list. So this sequence of assignments is a particular representation of the function that we're going to use, all right? To backpropagate, we go through the list in reverse order, okay? So just to give you an example of a list, right, or a little piece of a list, we've got a variable x7, and it's a function of 2 inputs, right? And just my notation, pi of 7 are the previous inputs that it depends on. So it's this tuple of values. And the function we use here is the function that we applied, which in this case is addition. So using operator notation, but it's a function of 2 inputs. All right. So so to compute the function value, it's very simple, right? I basically start with my inputs, and then I go through and I compute all the rest of the variables, these variables in the list. Okay. And each one, I basically just apply the function to the appropriate inputs. So this is my notation for doing that. So that's the first thing we're going to do. We're going to evaluate the function. And then to differentiate, I'm going to go through this in reverse order. Okay? So the base case is basically the derivative of the output variable xn, the last variable, with respect to itself is 1. Okay? And then at each step, I'm going to use the chain rule. All right? So the derivative of the output variable xn with respect to xi, okay, where I is some point in this my sequence of operations. Well, what is it? Basically, I'm going to sum over the inputs of the derivative with respect to, the parents of xi, right? Okay. Now let's work this out. So we're going to find the things of which I is a parent. Well, look, those are j, okay? So when I'm differentiating x2, I'll look at the things it's a parent of, right? I'll look at the derivative of those things with the derivative of the final output with respect to those things, all right? And then we'll do another kind of local step, which corresponds to the function that we're at, all right? So this is basically backpropagation. So the update we're going to do here is we're going to go backwards through the list, and we'll define the derivative of the output with respect to the ith variable, okay, this way, all right? So if you like, this quantity here is an error signal. We're propagating backward, and then we're actually computing the derivative of the function that was applied here with respect to the output. Okay, so here this fi is a function, so this is also a function, right? This derivative here is going to be computed in some previous step. Okay, so j is something that I is the parent of, so it's further downstream. So we'll know the derivative of the error signal at that point. Okay. All right. So this is the basic idea. And now we're going to kind of bounce back a little bit. We'll look at a somewhat more interesting realistic example. So my more realistic example will be feed-forward neural network. I know you didn't see that coming, right? And of course, you remember, like the neural network is this complicated-looking thing. It's like this big spirally graph. How do you write that as just a series of assignment statements? And the answer is, as I talked about before, is we use matrix operations. Okay, so as I said before, so one of the key steps we're doing here, for example, is we have a set of examples, maybe a mini batch of examples, and each of those are row vectors. And then I want to basically compute a weighted sum of those. That's sort of the one kind of key step in a neural network. And I can just do this by multiplying it by a weight vector. Okay. So we can write our neural networks down. And here's my Wengert list representation of a neural network. All right. So there's a bunch of things that are inputs. There's x, which is the normal input. All right. We're going to consider w, the weight vector, and the first bias term. Second weight vector and the second bias term, we're going to consider those all as inputs too. So those are basically given. All right. So what do? We do matrix multiplication, so we get the weighted sum of those things. I'm going to add a bias term here. All right. So we're going to add this. This is component-wise addition of two vectors. Well, actually, if this is a mini batch, then this is actually going to be a set of dot products, so we'll need potentially a matrix here. Okay, but we're going to basically add the bias vector. All right, then we'll apply element-wise sigmoid function. So tan h would be a good one. All right, and then we'll do the same thing again. We'll take those activations, we'll weight them, add a bias term, compute another element-wise tangent vector. All right, and then, as I suggested at the end of the day, on Tuesday, we're going to use this sort of modern loss function. So we're going to look at this function called softmax, which I think is on the next slide. And then our loss function will be cross entropy with that. Okay, so the cross entropy is with respect to some desired outputs. Okay, so that's not part of the input. It could be part of the input, but I'm treating it not as part of the input. So this is just the target value y. Let's say I have n examples, and I've got k outputs. Each of the examples has d features, and I've got h hidden units, let's say in each level. Okay, so let's just kind of step through what's happening here. So x is going to be a batch of n examples. So it's going to have n rows, one for each example, and d columns, one for each feature. Okay, and then w1, basically I'm coming up with weights for each of the hidden units, right? So basically I need one row for each dimension, and I need one column for each hidden unit. So that will basically mean that when I multiply this by that, all right, this quantity here is going to be n by h, right? So we'll have a set of hidden unit signals for each of the examples, okay, for each hidden unit, all right? Then the next thing we're going to do is add, so that will end up being the same size, so b better be the right size for that, all right? And then finally we're going to run everything through this tan h unit, so again, All right. Thank you very much. All right. Good? All right. Okay. Okay. So here, what's going on? We're computing x plus times w. That's a dot product. Then we're adding in b. We're applying this element-wise operation here. I'm going to guess that's exponentiation, and so on and so forth, right? So this isn't quite the whole graph, but this takes us down to the prediction step. So this is, what's kind of under the hood in Theano. So there, as I said, there are a bunch of other tools. So Theano is one that a lot of researchers use. It's built on top of Python, and it's been around for a while, so it's pretty stable. There are a number of libraries built over it. Torch is another one that some people like. There's some things it does a bit better. It's unfortunately written in something called Lua. So you have to learn Lua, which is apparently a very nice language, but it's not that widely used, so a lot of people don't know it. TensorFlow is a Google system. There's something called Autograd, which is a very Pythonic kind of clean implementation, but it's not quite as efficient or as mature as the others. Okay, so I'm going to spend a couple of minutes here breaking this down even a little bit further. And the reason I'm doing this is because, like I said, this is an assignment, okay? So I'm going to break this down. Like I said, it's really nice to be able to work with these matrix level operations, but it also adds a little bit of extra confusion to talk about them. So instead, I'm just going to talk about some really simple little functions. So I'm going to talk about this function for now, okay? So what would this look like if we're going to implement it in Python, okay? So we have a set of functions. Let's just call these string constants. So we've got add, multiply, and square. All right, and this is what our Wengert list looks like. All right, so to represent in Python, one sort of easy representation is I have the name of the output variable, the name of the function I'm going to use, and then a list of the arguments. Okay, well, I guess it's a tuple of the arguments. So I have a list of all the things I'm going to do in Python, just sort of coded as strings. All right. So this is sort of the intermediate thing we want to get. Now to compute with this, it's pretty simple, right? All I have to be able to do is evaluate each of these primitive functions, okay? So for each function on this list, I've got to basically tell you how to evaluate it. So for add, we'll just have a little Python function that returns the sum of two numbers. For square, we'll come up with another one that multiplies. And I guess that's all I need for this example, right? So to evaluate, I'm going to start off with a dictionary that maps the input variables to their values. So if I want to evaluate this at x1 equals 3 and x2 equals 7, I just start off with this dictionary. And then at each point in the list, I'll pick up the right function to apply. And then I'll apply it, which in Python you can basically just do like this. Okay. So that's the basic idea. And then for backpropagation, we need a little bit more. Okay. So for backpropagation, I need the derivative of each function. So that's another function. And I need a derivative for each input. So there's this other structure. So G is basically the functions I need. Okay. So dg is the derivative of those functions. Right? So add's got two arguments, so there's a list of two derivatives, both of which are pretty simple. Okay? And for square, there's a list of one because it's a unary operation. Okay? And the code is similar. So there's going to be a delta for each variable in the list. I'm going to start with the output, so the last thing in the list. Right? And then basically I'm going to go through the list in reverse order. Okay? And I'm going to look at each argument at each point. I'm going to compute I'm going to push back an error signal to each argument. So for each of the arguments, I'll figure out what derivative function to use. So this is the derivative of function g with respect to the ith argument. All right, so it'll pick out one of these things or one of those things, right? Okay. little complication here. So something could be the parent of more than one function, all right? So if I compute z1, I can use it multiple times further down the list, right? So every time I use it, there's a different signal, that's a different error signal that's being propagated. So how do I combine those error signals? The answer is you add them, okay? So the delta is actually going to be summed up, okay? Whenever you get a new delta for a variable, you'll increment. So here we're basically incrementing the delta, okay? So, so for just scalar constants, Python has like some, there's something called the default that lets you do this automatically, but we want to think about this explicitly and think about the fact we might have to initialize this because, of course, we might be working with some complicated data structures like matrices further on. Okay, so we basically add to the delta for this ith input, and we take the delta of the output and we multiply it by the derivative. Okay. So, once again, not to belabor this too much, what's actually going on here? All right, so this is just using the chain rule. All right, and this is sort of how it's using the chain rule. So if I have a Wengert list like this, so just simple linear sequence of operations. So I apply function 1 and then function 2, and then I chain it all the way out to function m. Okay, if I wanted to differentiate this, I could use the chain rule repeatedly like this, right? So the derivative of the output with respect to the input z0, right, is basically the derivative of the output with respect to the previous computation, and then the previous computation with respect to z0. That's the chain rule, right? And then I can repeat that operation over and over again until I get some long thing, all right? So let's just step back for a second and realize what this means, okay? So this is actually defining a function, okay? So this is saying what function is computed by this derivative, okay? That's a function. And this is also a function, right? Okay. Just to sort of like make things concrete, I'm going to write those functions down with like a variable like h sub ij rather than this, Leibniz notation thing. So let's just clarify what this means. This means that that function should work, right? I would get this sort of equality for every input, right? So when I say that this holds, okay, what I'm really saying is that for every a, let's say take a and I compute a1 is the, I guess this should have been f1 of a0, right? And then a2 is f2 of f1 of a0 and so on and so forth. This is the function I'm computing at the end of the day, right? So what this is really saying is basically for every input's a, right, the h sub m comma 0 applied to that function is this, okay? When I give you this chain rule, I'm saying this, all right? And this is exactly what we're doing, essentially, in our BackProp algorithm. In fact, we're doing this, and we're doing this repeatedly, right? So we're going back and back and back and back, right? And we're expanding out this, this product. And when we're expanding it out, what we're essentially doing is we're looking at, this is the error signal going in from, and so on and so forth, right? So what we're really doing is we're computing this product this way, right? So first we multiply the first two, then we multiply that with the third one, and so on and so forth, right? And the deltas we're looking at is this a prefix of this multiplication, right? So it's a multiplication of the first few things, all right? So this is the case for a chain. Obviously, a little bit more complicated when you get to a tree, but this is why this algorithm sort of makes sense. Okay. All right. So in the assignment, you got to do some of this yourself, and you don't have to do some of it yourself. So the part which is kind of tricky and programmatic and Python-y and not particularly a machine learning thing is actually getting from the some sort of reasonable readable, easily programmable representation of your function to the Wengert list. So that's like sort of a little compilation task. So we've done that for you. Okay, you don't have to do that. I'll explain to you kind of what is under the hood just for the, the sake of your education. So what you're going to do is you'll write code like this. This is kind of ripped out of the Guinea Pig code. So you'll define something. So here, this is just computing the area of a triangle. Okay, so you'll define a couple of inputs. So H and W are inputs, the area is a function of those inputs. So you have a bunch of functions, and you'll define the functions up here. Okay, and what you'll do is you'll create this object, an instance of this object. You'll call setup. All right, and that will give you something that you can do things with. So XM is expression manager. Okay. So the main thing you do is you call this operation sequence. So this will give you a sequence of a Wengert list to compute area. All right. So in this case, it would probably give you something like this. So it would say, here's a temporary variable, which you get by multiplying H and W. And then you have that, and that gives you the area. Okay. So to make this work, there are a couple of data structures. So these things, H and W and area, are called registers. So there's an object for each of these. Registers, we've overloaded operators on registers. So if you combine two registers with one of the built-in operators, it will basically construct a function. Right? That function doesn't have a Python variable name associated with it, so that's why you end up coming up with this hidden variable name, which they're all Z's. So don't use like Z1, Z2, and so on in your functions. That will be a problem. Okay. So the way this works then is we have these registers. There are a few different kinds of registers. So each register has a name, which might be something you have to assign at the end of the day. And there are a couple of different things they can be. They can be inputs. They can be parameters, which are really just a sort of special flavor of inputs. Or they can be the result of an operator. So an operator is sort of the other data structure here. If it's an operator, then there's some operator that defines it. The stuff you don't have to implement is sort of like auto-naming these things. So the name area came from this Python class variable, and Python can do that automatically with introspection, so you don't have to worry about that. So here's one case where the name's been sort of invented. So what do the operators look like? So half and multiplier here are operators. And every instance of an operator basically points back to the registers that are its output and also its inputs. So what gets built at the end of the day here is you have these registers and these things that are defined in terms of other values. There's an operator, and the operator tells you what function you're using. It's just a little structure, right? It tells you what function you're using, and then it points back to the inputs and also points to the output, which would be this one. Okay. So this is sort of the basic structure you use. And when you're defining your functions, it's actually pretty simple, right? So all the function has to do when you're creating the Wengert list, the only thing it knows you have to tell it is basically how to set up this little data structure where things are pointing back and forth, and there's a little function that does that. So when you're defining your function, you'll basically say what the name of the function is and what the arguments of it are. So it's pretty simple. So you're still following when I like drill in just a little bit more. So this is almost all the code. All right. So there's an operation, okay, and like I said, it basically has three things: a function, and arguments, and an output register. That's where the output's going to be stored. All right. So we initialize it with the function and registers, and we have to insert the output register later because it's kind of a cyclic data structure. All right. Then I've got a register, so it's got a role. It's got a default value, which actually you should always use for the assignment because it's helpful for testing. There are basically only a few types of roles that are allowed, so it can be an input or a parameter or an operator output. It's got a name. If it's an operator output, this is where it's defined. This is the operator that defines it. Okay, and that's a default value that can get filled in if you want. All right. And then to do operator overloading, we basically just map these things to some functions. All right. So these are what the default functions are. So there's a function that gives you an input and one that gives you a parameter. And then the operators that I've predefined basically call this little thing. And sort of basically what you're doing is you're plugging in a Wengert list with 2 arguments here, and the name of the function is quote add. So that's kind of all there is. So and I guess the register defined by function I kind of already showed you a little bit back, but it's basically this, right? It returns that structure. And then finally, after you've created your expression manager, you have to call setup. And what that basically does is it basically goes in and names the registers. So this is not too important to understand, but it's just using a little bit of Python introspection to find out if they're variables for either the instance that you're pointing to or the class, and tries to use those if it can. And then, of course, the last thing is to create the operator sequence. All right. So here's a slightly simplified version of that. So you give it the name of a register, and you start at that register, and you basically traverse downstream until you get all the inputs. And while you're doing that, you output the sequence of operations in pre-order. Okay, so this is what the code looks like, and here's sort of a very simple sample. I'm going to start out by subclassing my expression manager functions. So I'm writing my own functions, so I inherit all the ones that are there. And I'm also going to add, let's see, half and square. And this is just pointing to one register with a different name, just for fun. Once I've got these functions, I have to define how to evaluate them and how to differentiate them, right? So this is how you evaluate them. This is the G functions. So we've got a function for each of these things: add, subtract, multiply, half, square, and alias. And these are the derivatives. So all the binary things will have two derivative functions. All the other ones will be just defined with just one derivative function for the one argument. When I call these things, I'm passing in a little bit more information. In addition to just the inputs, I'm also passing in the output, because sometimes that's useful when you're defining the derivative. And I'm also passing in the previous delta. So what you're really returning is the product of the previous delta and the derivative. And again, that's mostly important in matrix operations where the multiplication operation you do is not always just like a multiply. So then here's the actual code for a eval. So I gave you sort of the pseudo code for it. We've got the destination variable, the function name. These are the inputs. We basically figure out what the values are here, okay, using Python's built-in map function over the input names and looking up the values from a dictionary, right? Then I figure out what function I want to apply. This is basically applying a function to a list of values. That's Python's way of doing that. And that gives us a result, which we store in the dictionary. And then for BackProp, it's almost the same, okay? We look at the delta of the destination. We figure out what the values are, and I'm actually going to stick delta onto the front of that. Then I'm going to basically go through each of the inputs. I'll call the appropriate partial derivative with the appropriate inputs, and then I do my increment for the delta. So that's the code that uses it, and here's like one final example. This is one way of using this. So in Guinea Pig, what you usually do is you define a class, and all the views that you define are just class variables, okay? And this would be sort of the corresponding thing here. You've got a class variable for a house that's called H, and one called W, and one called target variable, and target area, and so on and so forth. What you're doing here is you're specifying how high the walls of a house should be, and how important it is to get close to the right height. And then I'm going to give you a target area, and you're going to sort of optimize it. So the loss is basically how close you are between the area, okay, and we're going to use a square loss here, how close you are to the target height of the wall, okay, multiplied by the height factor. Okay, so this is the loss function, right, for the parameters of this house, okay? And the house is actually just a rectangle h by w. Oh, what happened? Oh, okay. Can you hang on for a second while I update? Maybe I'll skip that. All right. Okay, so the house is basically just a rectangle with a triangle on top, like you drew when you were 2, or 3 maybe. A little kid. And then to do the optimization, here's a little bit of gradient search. Okay, we start off with some initial dictionary. Okay, so H is my house. All right, I want to give it some initial values. I want the target area to be 200, maybe 200 square meters, I don't know. Right, and then I form the Wengert list, and then I basically go through here. I do back propagation, and it gives me a dictionary of all the gradients. All right, I pick out the ones that are parameters, and I update them. Here's a cooler example, all right? So this example has a loop, okay? So in Guinea Pig, if you want to do a loop, what you do is you create a little Guinea Pig program, and you call it over and over again from Python, all right? So you can't back propagate through that, right? So how do you create a loop in something like a neural network? So here's how you do that in this framework, all right? So I'm going to start off by creating an instance of an expression manager rather than subclassing it. All right, so this basically means whenever I talk about the variables, I've got to put x dot in front. Okay, so that's a little bit more tedious, a little bit more typing. So I'm going to say there's a couple of parameters here. There's an area and a height factor. So my skyscraper is actually going to be a whole bunch of rectangles stacked up on each other. I want to optimize the area of the skyscraper, okay? So I'm going to tell you how many floors to build, okay? So yeah, so I'm going to start out, 0 is an input that has a default value of 0. And there's something that points to an area register. Okay, so this is a Python variable that points to a register. All right, this is why you have to know all this stuff because it's a little bit complicated. So this is a Python variable that points to a register. Initially, it's just a 0 register. Okay, and then for every floor, what I'm going to basically do is I'll first compute the area of that floor. So that's h times w. I'm going to give it a name. If I didn't give it a name, these would all be like z1, z2, z3. That's not a problem. But you can give it a name if you want for debugging purposes. So I'll just plug a name here. Okay, it'll be floor whatever. Okay, and this now what I want to do is I want to take this and I want to add it to the old area. So what I'm going to do is I'll take the old area, which is pointed to by my variable area register. Okay, and I'll add it to floor register. That's going to give me a new register. All right, so this is the running sum of the areas. Okay, so this is always going to be basically a Python variable that talks to a register which isn't named yet. All right. So when I'm done with this loop, I basically give it a name by assigning it to an instance variable. I write down the loss function the same way, and that's basically it. Okay. So this is a lot. There's a write-up about the Autodiff stuff, and the assignment coming out Thursday also has pretty detailed instructions. But if you want to spend a little bit of time kind of taking a look at this beforehand, feel free to look at the examples. Are there questions? All right. I want to talk a little bit about some of the things that people use with these sorts of tools now. I actually, in the slide deck that I have a little section on recurrent neural networks, and I have another section on recurrent neural networks. I'm going to tell you right now we're not going to get to both of those, which is kind of what I expected. So how many people have studied convolutional neural networks in another class? Yeah, okay. We'll talk about them a little bit. Okay, we'll get to it probably Thursday. All right. So, so what I described so far is good for building, let's say, a multilinear network. But what do you want to do with these things? What are the sorts of more complex operations that you'd like to do that will exploit this kind of power to write down complex functions in a differentiable form? So here's one, which is basically predicting sequences. Okay, so this is pretty good for doing a prediction if I have a fixed number of inputs and a fixed number of outputs. All right, what if they vary? So one thing we can do is we can basically take this sort of network and we just can copy it over and over again, right? So that's one possibility. So let's say I'm predicting a sequence of things like I'm looking at a sequence of words in text, and I'm trying to predict whether each one is what the part of speech of each word is. So I could just basically treat them as a whole bunch of separate problems. But if I want to exploit some notion of what effect the sequence has on the outputs, then you might want to do something a little bit fancier. So one natural thing to do is say, well, let's take the output of this first thing and have it also be fed in as an input to the next thing. So at every point you're getting 2 inputs. Well, every point past the first one you're getting 2 inputs. One is the actual input that you see at that point in time, and the other one is some summary of the state just before you saw that input. And from those 2 inputs you have to produce an output. We have a start marker and an end marker, and in between we're passing some information that tells us what the context is from one unit to the next. So this is a really simple idea, and it's basically just the same multi-layer neural network, and then you copy some inputs here and you sort of pass them in here. Okay. So the problem with this, I mean, it's very straightforward and natural thing to do, but if you have a long sequence, it's really, really deep, and you run into the vanishing, exploding gradient problems. Okay, so it's really hard to train. All right, so for a long time, but really sort of becoming much more popular over the last few years, there's been a variant architecture called long-term, short-term memories. The basic idea here is you can fight back against the kind of vanishing gradient problem by having, rather than having an output that's computed by kind of a standard network representation, basically adding the depth of that network every time, you have a slightly different architecture. So what you do is you've got basically one context vector that sort of gets passed all along this chain of hidden units. Okay, and that one context vector is modified at each point, but only a little bit. Okay, so this is the basic idea. So this is taken from this nice blog post from a couple of years back. So these are all his pictures, just my explanation. So the notation here is this is a little neural network layer. So this is like a unit that's happening. All right, and not all of these are shown, but these are sort of the key ones. This is a pointwise operation. Okay, this is just copying things over. This is concatenating two vectors. This is copying two things over. Okay, and sigma here is the usual logistic function. So the key thing there is the output is between 0 and 1. All right, and tan h is another common logistic function. And the key thing there is the output is between +1 and -1. So roughly, the things that are passed through a sigma function are Boolean, or are intended to be thought of as Boolean things. And the things that get passed through tan h are thought of as data. Okay. So this is the basic idea. We have this big bus of information that sort of gets passed around. That's the long-term memory. And it's only modified in sort of structured ways. It's modified the same way by each unit. Okay, so there's this little subnetwork that happens in each unit, and that's replicated all the way down the chain. What happens here is essentially conceptually two things. One is you make a decision about which things in this memory you want to forget. So the memory is going to be a vector. Let's say it's a vector that's 10 units long. You can think of that as 10 bits of memory. So that's what you're remembering. So you'll multiply it by a bit vector, which will tell you which bits you want to forget, right? Then you'll compute another bit vector you might want to store in the memory, okay? And that will get inserted. And the way you insert it is, you basically add, all right? So if you multiply by 0, it's forgetting. If you add, you're putting a new value in it, okay? And what's in the memory is basically data. So it's it could be positive or negative numbers. So that's sort of the intuition behind it. Once we've done that, we take that memory state. We have a new input at this point. All right. So that input is used first to decide how to modify the memory. Okay. But it's also used to compute a new value. Right, and we're going to combine this with the memory, and that will basically determine what our next output is. And then that next output also gets passed in, okay? So this is kind of the long-term memory. This is sort of the short-term memory. And the idea is we don't really care if the gradients for this input sort of fade back because we've got this thing. And the gradients for these are somewhat more stable because of the way these operations are defined. So just to kind of walk this through, we decide what to forget. So this is a vector. So a 0 means to forget that particular bit. All right. So we basically take the last input and the current output. We concatenate those. That's this operation here. So we just concatenate these. We multiply it by a weight vector, and we add a bias term, and we apply sigma. So basically, we just do a little multi-layer perceptron, one hidden layer. Well, not even one hidden layer. We just basically do a linear transformation of this, all right, with a sigma, and that tells us what to forget, all right. Then we also make a similar operation to figure out what we're going to forget. So what we're going to insert, okay. So first we decide what bits we're going to insert at, okay. So this is the same sort of operation, but with different weights, okay. We're looking at the last state and the input, and we're adding a bias term, passing it through some weights, and we're, doing a sigma. So at the end of the day, we get a Boolean vector, okay? And, if we were going to insert something, what would we insert? Well, that's another, linear transformation with a tan h nonlinearity, okay? So this is also like sort of a one-step neural network that tells us what information we might insert. But then looking at that, we look at that content and we decide whether we're going to store it or not. As follows, okay, so the new content that actually gets written into the long-term memory, first we look at the old content and decide which bits to forget. So if f is 0, then that will get set to 0, and the closer it is to 0, the smaller, the less impact we'll have for the previous time step. And then there's the stuff that we insert, and that will get added to that. So we forget some things, and then we add some other things in, okay? So that gives us this output. So that's the next stage of the long-term memory content, all right? And then we have to figure out what we're going to output. So again, we take the last hidden state and the current input. We do a neural network layer. So this is basically telling us what bits we're going to output. So at the end of the day, we turn this into a Boolean. Okay. What we're going to do here is we're going to take HT and we're going to basically output some appropriate bits of the this memory content. Okay. Okay. So then that happens. So this is basically what part of the cell to output, and this is taking the bits in the cell and putting them into a positive negative range. Okay, so this is basically what happens in each cell. All right, and at the end of the day, you end up with something that looks like this. So this is the implementation essentially, right? Using Wengert lists and a few matrix vector operations. So this is what it looks like inside an LSTM, and the last thing is the loop that you write over these things. And typically the way the loop works is you do it for a fixed number of iterations, and if the input is too short, you pad it, and if it's too long, you throw away the extra bits. All right. So here we figure out what to forget. We figure out what we want to insert using that formula. We compute our hypothetical insertion, so we're not actually going to add this, but we might add this, right? And then we finally do the appropriate update to our long-term memory, okay? And then finally here we decide what we're going to output from that long-term memory and pull it out, and that's the next stage of the output. So this is basically what the implementation would look like in outline. Okay, so these are actually quite general. So you can use them for a number of different tasks. So you could have a one-to-many thing. So like for image captioning, you might pull in, this might be, say, the output of a convolutional network, and then you've got a bunch of LSTMs that will generate a bunch of outputs. So you could have many outputs from one input, right? You could look at a long sequence of things and output just one value at the end, right? So you could look at, say, like a long document and classify it into one of several categories. That's the assignment, or part of the assignment. You could do many-to-many, right? So you could take some input and output another output. So, so for example, you could read in a bit of Java code, and you could output the comments on the Java code, right? Or you could do something like part of speech tagging, where it's exactly a one-to-one map, but with correlations. So here's some illustrations of what you could do with this. So here's a particular LSTM training process of characters. So each character is encoded by a few bits of input. So here we've typed in HELL, okay, and this is trained by taking some real text, and what I'm going to do is I'm going to output the input but shifted by 1, okay. So we're trying to get an E here and an L there and an L there and an O there, okay. And in between we have an LSTM. So at test time, what we're going to do is we're going to pick some start character, and then we're going to generate the next character, maybe with a little bit of noise added, so we get something interesting. So here's some actual examples of what it does. This is kind of cool. So this was trained on Shakespeare, and this is stuff that's generated from Shakespeare, from that model. So this is not actually Shakespeare. I should not sleep, and who is but a chain and subjects of his death. It sounds kind of like Shakespeare to me, but I'm not an English major, so I really can't tell the difference. To be fair, you can actually get these with simpler models. So there was this was from this blog post, the effectiveness of recursive neural networks. And these examples were taken from that. Somebody posted a follow-up where they basically did the same thing with just unsmoothed, n-gram, character level n-gram models. And they also look kind of good, right? So this is, also not unreasonable. But they can also do other things that are a bit harder to do. So this is recipes, trained on a whole bunch of recipes, so it generates kind of random recipes. So I'm not sure you'd actually want to eat these, but they look kind of recipe-like. Again, you can do pretty well with just character level things. But here's something actually that's sort of astounding. So this is trained on a big corpus of physics articles, all right? And this is generated from that and run through LaTeX. So it's actually learning, to sort of correctly delimit mathematical expressions, right? And it's doing that over and over again. It's coming up with these things like XX prime and so on and so forth. So this seems very surprising. Another thing which is kind of surprising is training it on code. So this is training it on a lot of C code, all right? And again, you see a bunch of things that you wouldn't expect that you could do easily with a kind of statistical model. Certainly, things like these sort of like nicely balanced comments that have English in it, well, almost English. The kernel blank book will co-eld it to user space. That sounds like a comment. I don't think it is, right? And then, balanced curly braces and so on and so forth. So these are things that, like the character level n-gram model, just couldn't do at all. All right. So I actually have 5 more minutes, but I'm not going to do convolutional neural networks in 5 minutes. So I'm going to stop here. I'll stick around here for questions in case people have them for like 5 minutes, and then we'll talk to you again on Thursday.